All right, how's it going, everybody? We are here today. I'm recording this video on Sunday, March 28th. Today we're going to be talking about section 3.1. We're getting started with week 10 here, starting our chapter 3. Chapter 3 is going to be kind of a big, meaty chapter here. We got a whole lot of math that we're going to do here, but one of the interesting things about this chapter is that we're going to be avoiding actually doing calculus with our math at all costs. We're going to find that we're actually going to do a whole lot of simple linear algebra this chapter here. In chapter 3, what we're going to be studying is systems of planar, linear, first order, autonomous differential equations. We've got four modifiers on this statement about systems of differential equations here. Fortunately, all these words are pretty dang easy for us right here. Planar. Let's kind of identify a couple of these here. When we say planar, all we really mean is we're going to talk about 2D stuff. It's totally possible that we could have systems of 3, 4, 5, 100 differential equations out there. But as you might imagine, as soon as we have more than two variables, it gets very difficult for us to interpret things graphically. We also need some more calculus rules associated with calculus 3. That is technically not a prerequisite for this class, which is part of the reason why our focus on this class remains with two variables, two dimensions here. We're talking about linear differential equations here. Linear in x and y. What you can see in our example system right over here is we don't have things like square roots or squares or anything like that. First order stuff associated with x and y as far as powers. Our first order means our number of derivatives. Right? We're not looking at second derivatives or anything like that yet until the end of the chapter here. And we're talking about autonomous things, right? Autonomous differential equations. Remember that this means algebraically for us, no dependence on t. And remember that graphically, this means solutions won't intersect. All right, so we get an algebraic and a graphical statement about what autonomous means to us. Autonomous means we're never going to see the variable t show up in our differential equation over here. It also means that when we go to graph our solutions, none of them will ever intersect each other. We'll know that solutions bound other solutions and won't cross over them. So, two things that we should immediately point out about these systems. One, all linear systems, since everything we're going to look at in since the vast majority of everything we're going to look at in chapter 3 looks just like this guy right here, you should notice right away by super quick visual inspection, x and y both being equal to 0 result in both dx dt and dy dt also being equal to 0. Therefore, xy equal to 0, 0 is guaranteed to be an equilibrium solution for every single one of these systems that we're going to look at in chapter 3. Ultimately, one of our biggest goals of chapter 3, I'd say there's kind of like two or three large goals overall with chapter 3, and one of those three major goals is to classify the equilibria located at 0, 0 for any linear system. That's going to be probably our biggest single goal of the whole chapter, but there's a couple other things we're looking at here as well. The other thing that we should notice is that we set up some new vector notation to notate our differential equations in chapter 2. And we want to notice that with our systems of linear differential equations here, it's very well suited to that form of notation here. So some of the statements that we made were a couple things. One, using capital Y with a vector symbol to indicate the variable vector x and y. That's one thing that we've already stated. Another thing that we could do here is we can indicate the matrix A with these coefficients of A, B, C, and D. So it's a 2 by 2 matrix A right there. So it looks like we could use these two definitions here to rewrite our system of differential equations much more simply as the derivative of, that's capital Y with a vector symbol, so that's the derivative of each variable with respect to t, is equal to, with the matrix A, the coefficient matrix A, times the variable vector y with the arrow on top indicating that that is a vector there, which we could also write as capital F of y, where capital F is sort of intended to be sort of like the function vector, where it's little f of xy, little g of xy as the two functions that we're considering here. And you should notice, for those of you that maybe have forgotten some of the kind of our linear algebra basics here, that when we do our matrix multiplication here, the coefficient matrix A, B, C, D times the variable vector xy. Remember that when we do this matrix multiplication right here, we do the first row times the first column, and we add up all the terms that we get. So first row times first column. This is the dot product of the first row and the first column should be A times x plus B times y. The second row times the first column gives us second row first column in our output over here. So that's C times X plus D times Y right here. All right, so you can see that this is an appropriate matrix multiplication way to represent the equations that we have associated with our differential equation. And the thing that's really nice then is that we get to use this much more compact notation to indicate any general system of linear differential equations right there. Much more compact than writing our derivatives, than writing our multiplications and our additions and stuff like that. So this entire chapter, I'm going to use the verbalization of the A matrix, which is always representing our coefficient matrix of lowercase a, b, c, and d, the four multiple coefficients of our variables x and y, and our two differential equations, dx dt and dy dt. Real compact way to phrase this. So our A matrix is, again, something that we're going to talk about all semester, or all chapter here at least. So anytime you hear me say A matrix, I mean the coefficient matrix ABCD right here, which we often denote with this capital A that we're looking at right here. So the thing I want to say before I kind of slide away from these statements here is this. This seems outrageously particular, right? This is super specialty here. We're not just looking at differential equations. We're not just looking at systems of differential equations. We're looking at systems of planar, linear, first order, autonomous differential equations. And my question to you, or what I'm thinking you should be asking me right now, is how is it possibly the case that it's worth our time to spend like a quarter of a semester looking at this super narrow focus of what's going on in differential equations? This is crazy particular here, right? One of the things that we're going to be doing with this in chapter 3 is we're going to look at this very special case of systems of differential equations here in chapter 3. And we're going to do what often ends up being the case in math, is realizing after the fact that all the techniques that we learned and the conclusions that we've drawn from chapter 3 actually end up applying to lots of things that don't just have these classifications, with a little bit of a modification to the math that we've done here. So while this is a very special case scenario right here that doesn't necessarily cover lots of meaningful real world applications, all those things are sort of like one step adjacent to this. And again, what we're going to see in chapters 4, 5, and 6 is that when we run up to things that are a little bit different than these guys right here, that we're still going to be able to take our intuition and what we learned here and apply that same type of concept to those scenarios as well by making small modifications to the things that we did in chapter 3. So this is very special and particular here, but it is going to generalize well to scenarios outside of just our planar, linear, first order autonomous systems out there, right? This is very specialty right here. So before we really get started here, let's take a look and see what is it that we're going to see out here in chapter 3 altogether. Chapter 3 is 7 sections that we're going to cover here. It does go out to 3.8, but 3.8 gets away from our planar stuff. It goes into 3 dimensions right there. We're going to have a much more difficult time looking at that, which is why we're not going to be covering that in this class. So what we are going to see is the first 7 sections in chapter 3. This week 10, we're going to be covering sections 3.1 and 3.2. This is sort of our setup sections, as things often go in our math textbooks here. We're going to get lots of definitions and theorems associated with these systems of linear differential equations, kind of their properties and what we can expect to see from them. Once we've kind of laid that groundwork, we're going to recognize that we then do have access to the tools that we need to analyze these equilibria that are going to exist at the origin. So sections 3.3, 3.4, and 3.5 are going to cover, those 3 sections are going to cover essentially all the possible classifications that we could see of our equilibria at the origin. By the way, this was sort of one of your midterm questions there on your programming question on the midterm. I gave you a couple linear systems and said, produce the picture. Look at, and in fact, you even went and looked at section 3.7 in your book, and you've seen part of our summary table. But as I suggested to you in the problem on the midterm, that only covered sort of our primary cases, but there's lots of sort of fringe cases that are meaningful, that are like our transition cases. You should be thinking like bifurcations, our transition points right there. We're going to see some of those crop up as well. So I think we're going to get, I'm forgetting the number right now. We're either going to see 11 or 13 total classifications as opposed to just like the 6 or 7 that were in the table that you saw right there. But the remaining ones that are missing will be either very like extra easy because there's a lot of terms that are 0, or they're going to be sort of like our transition cases between one item in that table and another item in that table there. All right. So the other thing that we're going to see after we do 3.3 through 3.5, section 3.6 is actually not going to be about linear systems at all. It's going to be about second order differential equations, which we have considered a little bit right here. And what we're going to recognize is that second order differential equations can be rewritten as systems of first order differential equations, and therefore the analysis that we've done in 3.1 through 3.5 should have some meaningful way to directly relate to second order differential equations as opposed to systems of first order differential equations as well. So section 3.6 is saying, let's convert what we learned in the last 5 sections to also apply to this other scenario that doesn't necessarily seem to be directly related, and we will prove that they are very closely related and that we can use the same techniques to solve them. Finally, this is one of those things where we definitely deserve a summary section right here. What you're going to see is that in 3.3 through 3.5, you are going to do a mountain of math. And what we're going to see in 3.7 is that we're going to be able to condense everything that we just saw to stuff that you can straight up just do in your head. And I'm going to say, hey, here's a system of differential equations. Classify the behavior near the origin. And you're just going to like look at it and you're going to do 5 seconds of mental math and you're going to say, oh, it's a spiral sink. And you're going to be right. And so the summary is going to be a really important section right there. We get some really nice conclusions of how all these things tie together really, really nicely in 3.7. So I really, sometimes summary sections, I'm like, psh, skipping that one. Nope, this one's really cool right here in 3.7, tying it all together. And 3.7 is also going to give us a very nice close tie to some linear algebra topics if you've already taken linear algebra. If you haven't taken linear algebra, this is going to be something that you're going to see later and you're going to say, oh, neat, that's some stuff that I already knew right there. This might be my meaningful time to stop and say now. One of the things that I've seen happening at other universities around the country recently, one of the small shifts that I've seen in how these types of courses are taught, is that I've seen that lots of bigger schools have transitioned into teaching differential equations, this class right here, rather than offering it as like a, so I took it as a 3-credit class. It's a 4-credit class here because we cover a little bit more than when I originally took the class. And what I've been seeing is that a lot of schools are now offering a 5-credit version of differential equations, but that's because it is a combination class, linear equations, or sorry, differential equations and linear algebra combined into one course. It's sort of like 2 courses in one. It's a 5-credit class. And it makes sense because this chapter especially, you're going to see everywhere possible, we're going to substitute doing calculus with doing linear algebra instead. They're married very, very closely in this chapter here. And so I really think it's a really smart idea that schools are kind of creating that one like, oh, you're going to be an engineer, then you need both these anyway. They go together so much. Let's just teach them all at once in one big class. So it's going to make a bunch of sense why that's going to be the case here in chapter 3 for us. So let's kind of get started with our analysis. And what I want to say first is that I'm going to skip over this interpretation example because it would just be me repeating everything that the book says in a few paragraphs here. So you should go read this one. As you guys have seen, our book does a pretty good job of like creating one type of example and then following it for a really long time. So you can see how small changes modify, how new techniques are incorporated into it. The big ones that we've seen so far are 3 different population models that we've built. And the other one that we've seen is our mixing problems that we've touched on 3 or 4 different times. Every time we got a new technique, came back to the mixing problem, right? For the rest of this chapter, the book regularly comes back to this Bob and Paul CD store example. So they're going to say Bob and Paul are 2 guys and they both own CD stores on the same block in some shopping district out there. And the question is, how does the amount of profit that Bob and Paul's 2 individual CD stores earn affect the sales at each of their 2 CD stores? And so they kind of set up some examples here. They give you some values for lowercase a, b, c, and d, and they say, interpret this. What would this look like? How do we interpret these sales relative to these coefficients that we see right here? And what you guys know is that, CDs are purchased by hipsters. So maybe if your store is making a ton of profit, maybe that discourages your customers from coming because they don't want to shop at the popular place. Maybe it's the case that Paul doing really well actually brings business to Bob's store as well since they're on the same block. Maybe they're competing instead, right? There's lots of different ways that these 2 guys could have relationships with each other with their 2 different stores. And so you should read this. It's pretty simple for the interpretation out there. I just think for the sake of my videos being maybe only an hour instead of an hour and a half, that's something that you guys could read out of the book just as easily as I could explain it in the video right here. And I think it's worth it for you guys to take a moment to try and, think for yourself, how would I interpret these coefficients right here? So go ahead and check out that example in the book. We'll be seeing a lot more of Bob and Paul. They kind of bring those guys up over and over again in these sections here as their kind of repeat example, and they do a good job with that. So let's start with section 3.1 here. So again, this week we're going to cover 3.1 and 3.2 as our setup stuff, and then in the next couple of weeks we'll see all of our classifications fall out of our setups. So let's start where we usually start. by saying, if we don't know what we're doing, let's at least stop and say, where are equilibria located? We've already talked about our equilibria for our systems, just like with our single differential equations, just being where there is no change, where our derivatives now, two derivatives, are equal to zero. So first, let's kind of just recall our vector notation that's associated with these guys right here, to recognize that the 0, 0 case is definitely going to be there for us. So using all this vector notation that we've got, remember, we've said things like capital F of capital Y vector is going to be, that's our dx dt dy dt vector, which is the same thing as our A, B, C, D coefficient matrix times our variable vector xy right here. And we took all of this and then just wrote this in its slightly more condensed form of dy dt equals a y, right? So I'm kind of repeating a bunch of notation here just because this is sort of, in a sense, it's a lot of notation. It's one of, this is in the long list of things where I write it and people are like, yeah, okay. And then I ask them to write it and they're like, I don't remember how I'm supposed to be writing this. This will take a little bit of practice. You'll get more used to this over the course of this chapter right here, all this notation that we're using right here. And the thing that I think is important is don't forget like where these came from. I feel like what often ends up happening is by the end of chapter 3, everybody's down with this statement on the right, and then they occasionally forget that where this came from was actually some like written out dx dt equals dy dt equals equations here. Obviously, maintain that reference right there. So our equilibrium points are all right. So there, the ordered pair is such that our variable vector y, and I'm calling it y sub 0 right there. I'm kind of just giving a label to it. It's the variable choice that I'm making, that I'm expecting to produce zeros as my outputs, produce zeros as my values for dx dt and dy dt. So there are the values such that when we do our coefficient matrix A times our choice of variables, what we're getting out is 0, 0. This is our dx dt and dy dt, right? So there's our A times vector y equals 0, 0 for dx dt and dy dt here. All right. So first, you can easily see that making this choice of y to be 0, 0 is going to be a solution for every linear system. That's not that crazy. If you take our coefficient matrix ABCD and multiply it by the variable vector 0, 0, unsurprisingly, you're going to get out 0, 0 as the resulting vector describing our changes of x and our changes of y. So what I'm wondering is, are there other solutions other than just the solution at the origin, saying plugging in 0 for x and for y will result in 0 for dx dt and dy dt? That's sort of our trivial solution here, right? It's the one that's always going to kind of be there, because 0 just makes everything go away nicely, right? There's our trivial solution. Now what I want to suggest is, could there be a non-trivial solution? Is there some solution that's not just 0, 0 that's going to cause this to happen? So I'm going to suggest that x sub 0, y sub 0 is another potential solution. And although their subscripts are 0, I'm suggesting that we're looking for the solution that's where that vector is not equal to 0, 0, right? We're looking for maybe 5, 7 is going to be an equilibrium point. When might that happen? All right. So what we need to do is we need to say, well, we want to let dx dt and dy dt both be equal to 0 to go and find where this equilibrium occurs. And so I'm going to take my dx dt equal to 0 equation first, and I'm going to say, well, then this would say to me ax0 plus by0 should be equal to 0, right? That's dx dt equals 0 if our point is x0, y0 here. And I know that I'm going to want to try and solve a system of equations here, so I'm going to go ahead and solve this guy for x0, and we're going to substitute it into our other equation that we've got here, right? Because our other equation is our cx0 plus dy0 equals 0, all right? So let's go ahead. I'm going to solve this guy for x0. And let's go ahead and plug it in here and see what we get for our two solutions here, for our x0 and our y0. I want to know what they're going to be. So I'm going to get here a negative b over a y0 plus d y0 equals 0. And so now we can go ahead and solve for y0. I want to know what really is the value that we're going to get here, right? So I'm thinking to myself, I've just got two groupings of y0 right here. So it seems to me like I should be able to factor some stuff out. So I'm seeing here that I'm getting a negative bc over a plus d is how much y0 I've got right here. All right. So what I'm going to do is this. I'm going to take a look at now my zero product property for this guy, right? That's saying to me, I'm multiplying together two numbers and I'm getting out 0. So either one thing I can, sorry, I stopped mid-sentence there. I'm going to start over. One thing that could happen, apparently, to make this equation be true is that y0 would need to be 0. You should notice that if y0 is 0, then coming back over here, that guarantees that x sub 0 is also 0. Well, that's just giving us that trivial solution that we've already said, no, we're looking for the one that's not that, right? This is exactly the one we're trying to ignore right now. So it seems like the only other way that we get a non-trivial solution is if negative bc over a plus d equals 0. Now that doesn't look like any, that just seems like a ridiculous statement for me to make. So I'm going to do a quick brief little bit of algebra right now to rearrange this, and then I'm hoping that this looks like something that most of us do actually recognize here. I'm thinking to myself, first thing I'm thinking to myself is I don't like fractions, so I'm going to multiply this whole thing by a. Now, AD minus BC should be something that we recognize from any amount of linear algebra that we've ever taken right there. That is the determinant of the A matrix here, right? We've defined the A matrix right here to be this ABCD matrix. All right. Well, we just found that if the determinant of that matrix is 0, then there is going to be a non-trivial solution. All right. So, I think that this is a really good justification, by the way, that we've been kind of moving into this vector matrix notation for this because it now seems like some ideas from linear algebra, like determinants, are naturally cropping up in the math that we're doing over here, right? So let's kind of conclude what we just saw here. It seems like linear systems are going to have a non-trivial equilibrium, an equilibrium not at 0, 0, somewhere else, if and only if, the only way it can happen is if AD minus BC is equal to 0, if our determinant of A is equal to 0. So we're noticing here that AD minus BC is our predefined quantity in math out there. The determinant of a matrix, of a 2 by 2 matrix, is, I refer to this as the downs minus the ups. I think that's a really weird way to think about that. I think about a lot of things weird right there. That's the phrasing I use in my head when I compute a determinant of a 2 by 2 matrix, which you will do so many times this chapter, so don't worry, you'll get good at it once we get to those problems right here. We'll talk a little bit more matrix math here coming up because I know that some people are really comfortable with this and other people have seen only like the tiniest bits. So as we get into doing that bit of math out there, we'll come back to kind of making sure that everybody's on board with that. So again, I think this is a really good justification of why we've kind of swapped notations into this matrix vector thing right here, because we're talking about properties of a matrix when we identify that AD minus BC is a determinant of a matrix right there. So I feel better that we've moved into that notation because of this quantity of interest that we just found right here. All right. Can I not get this line right here? I can. So the converse of this statement now is to say that if we find that the determinant of the A matrix is 0, then the only equilibrium, or sorry, this should be a not equal to right there, right? Yeah, sorry, that's a not equal to right there. If the determinant of the A matrix is not 0, then the only equilibrium is located at 0, 0, right? And we saw this with our math right here. If we don't get that the determinant is equal to 0, then this statement is only true when y is 0. And we saw that if y is 0, then x is guaranteed to also be 0, right? So this converse of this statement is actually the one that's a little bit more interesting to us right here. If the determinant is non-zero, then the only equilibrium is at the origin, and therefore the only one that you need to classify is the one that's at 0, 0. It's actually going to turn out that the determinant of A being equal to 0 is really going to be sort of one of our like special cases or fringe cases that we're not actually going to see that often, where you should expect to see mostly non-zero determinants, and for it to be kind of a difficult thing for us to analyze once we do come up to that. I think that's in section 3.5 where we say, well, what happens if the determinant of A is equal to 0? Where are those other ones located at? And we're going to get some slightly surprising answer. It's not just going to be like, it's, oh, I solved it. It's at 5, 7. We're going to get a little bit of a weirder answer for that guy right there. That's coming out in section 3.5, right? So we can conclude that if A is a matrix with the determinant of A being not 0, then the only equilibrium point of our system is at 0, 0. And that's the thing that we're looking to classify, so that's good. So that says to me we can really just focus on this 0, 0 location for our classification of the equilibria, except for in the weird cases where the determinant of A does end up being 0. And that basically gets its own section devoted to it out in 3.5, so we don't need to worry about that too much right now. So this is kind of our first part of our analysis of this, is to say this particular case that we're interested in for this whole chapter, these planar linear first order autonomous differential equations, we know to expect that all of them will have an equilibrium at 0, 0. We know how to detect if they have an equilibrium anywhere else, and I have made the promise to you that in section 3.5 is going to be when we're going to discuss the only scenarios in which we'll see anything else happen. So that says to you, our focus for most of this chapter is classify the equilibrium at the origin. That one sentence right there is like the kind of the primary goal, I would say, of chapter 3 for linear systems here. All right. So what we now want to do is use this to help relate this to the overall general solution that we're going to see. What's a general system of equations that we can come up with that parametrically define all of those infinite number of solution curves that we see when we go to our phase plane plotters out here. All right? And the linearity principle is what's going to provide it for us here. All right? So let's talk about the linearity principle here. The linearity principle is I guess the mathematician perspective of the linearity principle, rather than like the differential equation, slightly more narrow focus on this guy, is really just to say derivatives, the operation of the derivative, shares some properties with the operation of matrix multiplication. That's in one sentence, that's what the linearity principle is doing. It's why it's working out the way that it is. The idea comes from the fact that derivatives play nicely with addition, subtraction, and constant multiplication. What you know is that if I have a function that is a sum of many functions, that I could either apply the derivative to, or I don't need to worry about that addition subtraction, right? In a sense, the derivative distributes across addition subtraction. You also know that if we have a constant multiple of a function like 5x squared versus just x squared, you can, in a sense, ignore that 5 when you're taking the derivative, and it doesn't really affect the overall result that you're going to get. You could either do that multiplication by 5 before you take the derivative or after you take the derivative, and either way it's going to work out just fine, right? So derivatives play nicely with addition, subtraction, and that's really one thing, addition, subtraction, and constant multiplication. It turns out that matrix multiplication feels the same way about these things right here, right? So here are the essential, so statement 1 and 2 are the two statements that are the linearity principle. What we are going to most often do is combine them into a single statement. That's what we get for statement 3, is the combination of statements 1 and 2. So statement 1 says, if we can find some function y of t, remember that's a capital Y of t, I'm not just defining one of our two variables. Capital Y as a vector is x and y. So if we can come up with our solutions to the system, and k is some constant that's out there, then it's going to be the case that k times the solution that we found is also going to be a solution to the system. We can multiply any solution that we found by a constant multiple. It does not affect whether that thing is a solution. It's still a solution if we've multiplied our solution by k. The other part of the linearity principle, so this deals with our constant multiples. This deals with our addition subtraction stuff that's out there, right? This says if you can find two solutions, y1 and y2, if you can find two different curves in our solution space in their equations, then it should be that you can add together those two sets of equations, add the x parts to the x parts, or sorry, add x1 of t to x2 of t, add y1 of t to y2 of t, then that vector collectively will also be itself a solution. Therefore, combining 1 and 2, we're going to see if we can find two solutions, y1 and y2, and any two constants, k1 and k2, then all linear combinations of y1 and y2 are also solutions. So this is, in general, what we would refer to as linear combinations of y1 and y2. Right? So whenever we use the phrase linear combinations, we mean all sums and differences of constant multiples of those two things, right? So you can add them, subtract them, take any constant multiples of them that you want. All that stuff collectively is going to work out to also be something that does satisfy the original differential equation as well. Number three is going to be how we're going to construct general solutions to differential equations. So kind of notice here what we're going to get from this. This is going to end up providing to us all solutions out there in the plane, all of them, which is awesome. So what this is really saying to us to motivate our next actions is we would like to come up with two solutions. And now they're going to require one extra little property, but that property is going to kind of come along with most of them by default, right? So if we can find two solutions, this says all linear combinations of those two solutions is also a solution. And we're going to see that this is actually going to provide us all solutions in the plane, motivating us to say, all right, in any system of differential equations, if I can just get two particular solutions, I'm essentially done. I can use those to form my general solution. So the question is going to be for section 3.2, what are the easiest two solutions we can find for any differential equation? And that's exactly what section 3.2 is going to cover. Right? So the proofs of these statements, of statement 1 and statement 2, are pretty dang easy. The book does them, and you should stop for a moment and prove them yourself as well. What we want to prove to ourselves is that a constant multiple being applied before we multiply by the A matrix is going to give us the same results as if the constant multiple is applied after we've applied the A matrix, right? This is sort of like saying, do you want to do the constant multiple before the derivative or after the derivative? We know from derivatives it doesn't matter. We want to prove that the same thing is true when we talk about our linear algebra operations here. Similarly speaking, this says we know that we could apply a derivative to a sum of functions. We also know that it should work out that we can individually apply a derivative to each of those functions one by one and then apply the sum afterwards. We want to verify that the same thing is true for matrix multiplication as well. So this is really proving which operations derivatives and matrix multiplication as operations have in common. And they don't have, obviously, derivatives and matrix multiplication don't just have every property in common, but they do have these two properties in common, and that's really meaningful for us. That says that a lot of the calculus that we want to do will be able to be replaced with some linear algebra instead. And even if you're not super pumped on doing linear algebra, is there anything that's generally harder than performing multiple steps of integration? And the answer is almost always no. So this is going to be good for us. This is going to save us a lot of time and effort here, this chapter for sure. So I would advise you to stop and try and prove both these statements right there. They're both relatively easy to do with a light bit of matrix multiplication and just algebraic rearrangements. No derivatives are happening here. And you can check your textbook. The textbook shows, I believe, both those proofs. Maybe just one of them in assigns one is a homework problem, but that just means I think it's in the back of the book then. So let's look at an example of this because this seems kind of weird and I feel like I made some claims that were maybe me getting a little bit ahead of myself right now. So let's look back at an example that we've previously seen. Let's see these statements in action right here. So that we can get a bit of a better feel for the linearity principle. And again, the linearity principle is going to be like our one guiding theorem that's going to provide for us our general solutions to systems of differential equations for this entire chapter. This is not just like some stepping stone for us. This is a cornerstone instead for all of chapter 3. Without the linearity principle, we'd be dead in the water right now. So this is pretty important right here. So let's look at an example. Back in section 2.3, if you can remember all the way back to, I mean, honestly, what was this, like almost 4 weeks ago now that we covered chapter 2 stuff because we've had spring break week, midterm week, and we had our 2 weeks of our numerical solving stuff out there. So way back in section 2.3, we looked at this system right here. This is exactly the same system we looked at in 2.3. And what we noticed was this is only a partially coupled, or I guess you could say partially decoupled system because this second differential equation had no x's in it anywhere. So this guy we can directly solve for y, we can easily find that y is going to be e to the negative 4t plus a constant plus a constant. We could then plug that function of t that we found for y in for y in our second differential equation, and then solve this as a linear differential equation using an integrating factor. It's exactly what we did back in section 2.3. I did that example. I wrote out all the math. If you want to see it again, go look at the section 2.3 notes, right? So we were able to solve this, and we had these constants in there. Constants from integration popped out. So we had these two constants, k1 and k2. We then applied two different sets of initial conditions to find two different particular solutions. So remember, in our phase plane, we're seeing there's an infinite number of curves. You can go to our bluffton.edu plotter and just click 1,000 times, and it's going to produce 1,000 different curves. We found two of those curves that were out there by plugging in two initial conditions. What we'd really like, though, is a general set of equations that could generally describe any of those curves that we might end up seeing out there in space. Not having to like literally list one set of equations for every curve that's out there in space. We want one general solution to the whole thing. Right? So what we want to do a little bit of, oh yeah, by the way, here's the two solutions that we ended up coming up with, two particular solutions, and they're associated with two sets of initial conditions. I think it was just 1, 0 and negative 1, 2 were our initial conditions here. I think it was x of 0, y of 0 was equal to 1, 0. And I think here we had x of 0, y of 0 being equal to negative 1, 2. I think were the two initial conditions that we had for those guys right there. So we plugged those in, we solved for k1 and k2, and we landed at these two solutions right here. All right. What I want to do is let's use the linearity principle to kind of investigate this a little bit further. Let's A, confirm that these individually are in fact solutions. Since this was like a month ago that we did this problem, let's confirm that I didn't typo anything and that these are solutions to this system right here. B, let's confirm that the sum of y1 and y2 is also a solution. That would be statement 2 of the linearity principle. Given two solutions, their sum is also a solution. And then for 3, let's confirm the third statement from the linearity principle saying we can also do constant multiples of the sum or difference of y1 and y2, and that should also work out to be a solution. So I'm coming up with a new y3. I'm defining it to be constant multiples of a sum or difference of y1 and y2, a linear combination of y1 and y2. I just kind of arbitrarily picked negative 1 and positive 3 as my coefficients on those guys. And let's find what y3 would be, plug it back into the original differential equation, verify that it as well is a solution here. So let's do A, B, and C right now, just to make sure that the linearity principle is working the way that we think that it should here. All right. So doing part A, we want to verify that these two solutions are in fact solutions to the original system here, right? So we've got dx dt equals, I'm going to rewrite this out right here, 2x plus 3y, and then dy dt is just negative 4y. So what we want to do is plug in this for x of t, right? And this is y of t right here. That's equal to right there. So I'm going to use 0 for y, and I'm going to use e to the 2t for x, and I want to verify that we're going to get a true statement right here, right? So we're going to do our y1 check. And that's going to show me that d here, let me write it like this. I'm going to do dx dt on the left. So that's the derivative of e to the 2t. That's dx dt equals 2 e to the 2t plus 3 times 0. I'm noticing here the derivative of e to the 2t is 2e to the 2t. On the right-hand side, 3 times 0 goes to 0, and we got 2e to the 2t. So my x equation, my dx dt has been verified. And then our dy dt, it says the derivative of 0 equals negative 4 times 0, and therefore 0 equals 0. So our y1 check is good. I checked that this y1 equation, right, or system of equations, is a solution to this system of differential equations right here. Now let's go ahead and check that y2 also works right here. Let's do our y2 check. And by the way, this is something where normally when I teach this class in person, I assign a vector hat captain because if you don't write your little vector symbol on top of y, then I'm thinking that you're actually talking about the variable y rather than the vector y hat that contains both x of t and y of t. So don't drop your vector symbol right there. It meaningfully represents that you're talking about a vector's worth of variables, not one of the variables within that vector. So keep that vector hat on there. So now we're going to go ahead and check this guy with this guy right here. So now my x of t equation is negative 4, or negative e to the 4t. So I'm going to do my derivative of x with respect to t. Here's my derivative of x. Should be equal to 2 times negative e to the 4t plus 3 times 2e to the negative 4t, right? And notice this is x, this is y, as pulled from this guy right here. This is my x of t, y of t for the second equation. All right. So let's verify that this is correct right here. If I take the derivative of this guy, it's going to pop down a negative 4. So I'm going to get a positive 4e to the negative 4t. This should be equal to negative 2e to the 4t plus 6e to the negative 4t. And I don't think I need to write one more line right there. You guys can see that negative 2 plus 6 is 4. All of the exponents on the e's are all equivalent to one another. So our x check is good. We now need to check that the derivative with respect to t of our y equation is going to give us the result from the dy dt equation, negative 4y. So this should be negative 4 times our y, which is 2e to the negative 4t. And I check over here, my derivative is going to pop down a negative 4, so I'm going to get a negative 8e to the negative 4t. And over here, we can clearly see this is also going to give us a negative 8e to the negative 4t. So it does look like we've been able to confirm that this y1 and y2 that we came up with like a month ago now do in fact satisfy the original system of differential equations. And we just plugged in x and y everywhere we saw x and y, right? X, y, 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 right? There's 5 variables of x and y mixed throughout there. We just threw in all the parts and we got equations that were all correct right there. So there's A. We confirmed that all of these are individually solutions. The next thing that we want to do now for part B is let's confirm that their sum is a solution. All right. So what I'm suggesting here is that there should be a new y, and I'm just going to call it general y hat right here because I, for some reason, named that y3. I should have called that y4. All right, let's do this right here. Let me do myself a favor. There, cool. Confirm that their sum y3 is a solution. So I'm going to say that y3 is y1 plus y2. So that means to me that y3 is actually the sum of each of these. So it looks like what I'm really going to get is e to the 2t minus e to the 4t as my x equation. I added together the two x parts. I'm also going to add together the two y parts, but one of them 0, so nothing exciting there. Just 2e to the negative 4t. All right. What I now want to verify is that this is going to work out as well for a solution here. So I think I've got all the parts that I need. So I'm now using this as my x of t, y of t. Let's go ahead and do it. So the derivative of x, so that's going to tell me the derivative with respect to t of my x component, e to the 2t minus e to the 4t, should be equal to 2 times my x component plus 3 times my y component. Am I falling off the side over here? I am, barely. Can I smidge myself on here? Sure, close enough. There we go. Is this true? Well, it looks like here I'm going to get 2e to the 2t minus 4e to the 4t. And that should be equal to, what are we getting? 2e to the 2t minus 2e to the 4t plus 6e to the negative 4t. And I am seeing here the 2's, positive 2 of them and positive 2 of them. That's good. I'm also seeing negative 4 of them with negative 4 of them right there. So I feel very good about that. I don't think I need to write out some more math right there. We can see it. That's definitely an equality right there. We can also check our y equation here to verify that it is all good right here. So we want the derivative of our y component, which is just 2e to the negative 4t, is equal to negative 4 times our y component, right? I'm just following exactly I'm just plugging y into this equation and seeing if it's right. That's all we're doing here. And very clearly, This is right because there wasn't even a y component to be shared from one of the equations. So this check right here just looks identical to the check that we just did with y2 a second ago right there. So we've done B. We verified that it looks like if you take the sum of these two known solutions, they worked out to also be a solution to the original differential equation as well. So by finding two individual solutions, we're able to construct more solutions that we hadn't found previously. This is really interesting. Now we want to say, let's take this a step further and let's say, listen, you could have actually done any constant multiples also of y1 and y2, and it still would have worked out for us right here. So I'm going to do negative 1y1 plus 3y2. Again, I just kind of randomly selected these coefficients right here. Let's call that y4, and let's check that y4 is also going to work right here. So for C, we're saying that y4 is negative y1 plus 3y2. And that's really going to be for us, y4 is going to be y1. y1 was the negative e is going to get negated, right? So we're taking the negative of y1, so I'm going to get negative e to the 2t. I'm going to get 3 copies of y2's x component. 3 copy of y2's x component is going to give me a negative 3 e to the 4t. We're also looking at taking the negative of y1's y component. So that's the negative of 0, so that remains 0. Finally, we're looking at 3 copies of y2's y component. 3 copies of 2e to the negative 4t, so we're going to get 6e to the negative 4t. So let's go ahead and check and see that y4 is in fact a solution to our system of differential equations, right? So we're going to take the derivative of our x component. And it should be equal to 2x plus 3y. So I've got 2 times our x stuff plus 3 times our y stuff. Taking my derivative over here, I'm going to get a negative 2 e to the 2t minus 12 e to the 4t. On the right-hand side, I'm going to get a negative 2 e to the 2t. I'm going to get a negative 6 e to the 4t. I'm going to get plus 18 e to the negative 4t. And you guys can clearly see here our negative 2 e to the 2t's are clearly matching. You guys can also clearly see here that our negative 12 is exactly the coefficient we should be getting from negative 6 and positive 18 right there with the e's. And wait a minute, did I drop one of my negatives right here? I feel like I've got a negative and a negative. Where's my... Did I do that before also, by the way? I did do that. Where's my... Did I drop... I feel like I'm dropping a negative on my powers or something like that up there. Is that the case? This is the case right there. Okay. Sorry. Back at the original right here. I'm sorry. That guy's got a negative in there. Let me see where that actually cropped up in our terms out here. So this should have been then, let me go back to this. Let me make sure that let's follow that change throughout right here, right? I don't see any of it right here. I do see it happening right here. Oh no, that was X right there. I'm not changing. Wait a minute. Yeah, isn't that? Is that not the solution that we had previously found? Oh no, sorry, I'm not taking a derivative on this right-hand side. That's why that doesn't matter right there. Look, I'm not taking a derivative right here. I'm just doing a multiplication by 2. The derivative was happening over here, and I did include the negative as I was supposed to right there. So this just gets a negative right there. This is fine. And 2 times that is 2 times that. That's fine right there. So that all worked out correctly. I just dropped that and assumed that those coefficients matched right there, which they didn't as I wrote them, but they did as the math actually suggested they should. And then here I've got the negatives on each of those guys. So that one worked out right there. Here, this guy deserved this negative right here. So this should have actually been a plus when I took the derivative there, right? And then over here, okay, and I actually had a wrong sign, and I just walked right past it a moment ago right there. This got the plus because the negative actually popped down with the 4 to make that a positive 4 right there. Here we can see we did have positive 6 of them and negative 2 of that guy with the negative 4 on it right there as well. There we go. Now I've got all the negatives in the right places and all my math. I even got some incorrect things in my math over here and then glossed over them. That negative certainly did belong there. So now that we've actually got this in the right place, now let's go ahead and fix this guy a smidge right there. That's got a negative, which means that's got a positive. Over here, this has a negative and that has a negative. And now we can see positive 12 came from positive 18 minus 6. Okay, I dropped one. Hey, get used to it right here. I'm going to make mistakes like that in these videos all the time. So are you guys right here. It's going to happen. That negative certainly is on that power right there. So the power of 2t was the one that was positive. Both of the 4s were the negatives right there. So, okay, we've confirmed the dx dt equation. Now we want to confirm the dy dt equation, and we'll have confirmed that y4, the vector y4, is in fact a solution. So now we just got to do our derivative with respect to t of our y, which is 6e to the negative 4t. And this should be equal to, according to our differential equation, should be equal to negative 4 times our y component. So that's negative 4 times our y component, 6e to the negative 4t. That's our y component right there. That's y of t. And we can see that this clearly is going to happen right here. Negative 24 e to the negative 4t equals negative 24 e to the negative 4t. Cool. So what we've shown right here is that in this case, now we didn't show that this is true for any of them, but I hope that it's believable. It's good evidence that this is going to work out in general since these coefficients weren't anything specially chosen right here. All linear combinations of these two known solutions, y1 and y2, will always produce more things that are also solutions to the differential equation, and we can verify just by plugging in a whole bunch of stuff, right? So we verified a bunch of different things were solutions here, not just the y1 and y2 that we'd previously found. And so it gets even better than this. Not only can we verify that we do get new solutions by adding them together, but given any two linearly independent solutions and any other initial condition out there in the plane that's not associated with either of our known solutions, we can determine values of k1 and k2 that will create a third solution that does pass through that desired initial condition. This really is saying to us that knowing any two linearly independent solutions gets us all of the solutions. Now, what I need to define here is what does it mean for these two solutions to be linearly independent. I'm going to show that kind of graphically as we look at our next example right here. But what this is saying to us is that as long as the two solutions that we've found aren't basically just a constant multiple of one another, if they truly are two distinct solutions from one another, which notice here, y1 and y2 are clearly not just constant multiples of one another. This has 0 for the y component. This has not 0 for the y component. So it's not possible for these to be linear combinations of one another. They are linearly independent of one another. So as long as the two solutions that we found, y1 and y2, the vectors, are linearly independent, we can use them to build any other solution that's going to be in the plane, not just randomly smacking them together and being like, I guess that's a solution. We can find the one that we want. So here we're saying we found already the solutions that we found had associated with them the initial conditions of 1, 0 and negative 1, 2. I know for a fact now that I can use just these two equations to come up with some linear combination of them that's going to look like y4, and it can pass through any desired initial condition that I want. So you want this thing to go through 416 comma negative 511? Fine, I can find the k1 and k2, the constant multiples that need to be tacked on to y1 and y2 to produce a solution curve that's going to go through that desired point. And that's really, really nice for us here. So let's see it in action with the example that we just looked at. So this is me just rephrasing this whole thing once again, right? This is the A matrix that's associated with the system that we've been looking at. This is 2x plus 3y equals negative 4y. You should notice that it matters that I include this 0 right here because it's in the x slot. If we're doing x first, then y second, we had no x's in our second differential equation. We had a negative 4y in our second differential equation right there. Right? So that was the A coefficient matrix we've been dealing with. We had these initial conditions where at time 0, our location was 1, 0 for the first. At time 0, our initial location was negative 1, 2 for the second. That led us to these two y1 and y2s that we've been using this whole time. I need to change this now. In fact, I'll change to y5 because we've already seen a y3 and y4. What if we want to know what curve is going to pass through the location to negative 3? So this is me saying, let's pick some other point in space. Is it possible for me to make linear combinations of these first two solutions to create a new solution that will pass through any other desired point? If we can do that, then that's going to sort of justify to me that it seems like we can arrive at any desired particular solution by taking the appropriate linear combination of any two linearly independent solutions that we've already found. And again, what this is kind of saying to me now is this. If I want to come up with a general statement that represents all possible solutions in the plane, I just need to come up with any two linearly independent solutions, and then all linear combinations of those will produce all the rest. So we can just do our k1 times the first solution plus k2 times the second solution, and that'll be our general representation of the general solution in the plane, which is really nifty. It puts all of the work on just finding two solutions, and that gets us all the infinite number of solutions that there are, which is going to then beg the question for section 3.2, what two solutions should we go and hunt for? And my question is going to be rephrased as, what's the easiest types of equations that there are? What graphs do they make? And you should say straight lines. We're going to see this in a graph here in a minute. I'm like holding off on the graph because it's kind of the sweet part of today right here. So let's go ahead and see if we can do this, right? What we're kind of generally saying is that we want to find some y5 of t that looks like k1 times y1 of t plus k2 times y2 of t, right? What we know is that y5 of 0 is equal to k1 of y1 of 0 plus k2 of y2 of 0, right? The only piece of information that we have for all three of these equations is what's going on at time 0. We've got it right here, y1 at time 0, y2 at time 0, y5 at time 0. They're all already identified, right? So what I want to come up with is a general equation for y5. And remember, when I say y5, I really mean the vector y5 that has x of t and y of t within it. I want to build it as a linear combination of the vectors, the solutions, the first solution that we've got and the second solution that we've got. But what my problem is I don't know what K1 and K2 I should pick to make it be the perfect one that goes through my desired initial condition. So what I'm going to do is I'm going to do just a tiny smidge of algebra right here to find it. Y5 of 0 is exactly the vector 2, negative 3. K1 is the unknown. Our initial condition associated with the first solution was 1, 0. Our initial condition with the second solution was negative 1, 2. And so this is really leading me to this system of equations. I've just written this in vector form, but it doesn't need to be in vector form right here. I'm really writing this as equation. 2 times 1 copy of 2 is equal to 1 copy of K1 plus negative 1 copies of K2. So I'll say minus K2. The other equation that we've built here is negative 3 is equal to 0 copies of K1 and 2 copies of K2. So right away, it seems to me that I can make the statement here that K2 is going to be negative 3 halves. And if K2 is negative 3 halves, so I'm going to give myself some more room right here because I'm going to copy and paste in a graph as well. Then I can then say 2 equals K1 minus negative 3 halves. Looks like negative 3 halves here. I'm going to want to add that over to the other side right here. Oh, sorry, that's an addition. I'm like seeing a number I don't recognize because I'm doing my mental math poorly. This is addition. So I'm subtracting 3/2 from both sides to be left at 1/2 for K1. And therefore, the claim is that it looks like 1/2 of Y1 uh, and minus 3/2 of Y2 equal to Y5 will pass through the desired initial condition of 2, -3. All right. So this is pretty cool. So just by doing a, like, I mean, real easy solve a system of linear equations right here, kind of algebra, we were able to come up with what are the choices that we should make for K1 and K2 to pass through any other desired location in the plane of, in this case here, 2, -3. So let's look at a graph of all three of these solutions right here, and we'll verify that this actually worked out in Desmos here. And by the way, I also, very importantly, because I want to be able to graph this in Desmos to confirm that it works here, Y5 should be 1/2 of what we got for Y1. So I've got to scroll up here. It's half of what we got for Y1. So that says 1/2 of e to the 2t 0 minus 3/2 of Y2. And our Y2 solution was the, and I got to fix this again right here. I'm smarter now. Negative e to the -4t and 2e to the -4t. No, it was 2e to the -4t. So what we're getting for this vector y5 is it looks like I'm getting here 1/2 e to the 2t, -3/2 is multiplying negative e to the -4t for a positive 3/2 e to the -4t. Down in the second term, the y values down here, 0 times 1/2 is still 0, so nothing there. And we're multiplying 2e to the -4t by -3/2, so it looks like I'm getting a -3e to the -4t. And this is what we're claiming our x of t, y of t solution is going to look like now. All right. So what I want to do is I want to first go to the bluffton.edu and check the phase plane plotter. Then I want to show you that the curve that we're going to see, because, so what Bluffton does for us is it allows us to just plug in 2, -3, but it doesn't tell us like what equation it was, right? So we want to see in Desmos that the equation that Desmos graphs for this parametrically defined series of equations is the same as the graph that we got just by entering in 2, -3 over at Bluffton, right? So what we're going to do is we're first going to go to Bluffton, then we're going to go to Desmos. Over at Bluffton, we're going to enter in the original differential equation, right? Same as the thing that we got from our A matrix, 2x plus 3y, and then -4y are our dx dt and our dy dt equations. I'm going to enter in all three of these initial conditions right here and kind of verify that we're getting the right thing. So let's go ahead and do that. So here we are at Bluffton here. I'm going to go over to my systems. We're going to do our 2x plus 3y is our first equation. -4y is the second equation right there. It's going to produce a phase plane for us out here. And again, what I want you, oh gosh, look at how chunky and terrible these are. Let's turn this on to the smart method here and make these a little bit smaller. All right, so what you guys know is that we can click a billion different places in the plane. There's a billion, right, infinite number of particular solutions that are associated with this guy. All of these have different equations, and what our hope is that we can come up with one general equation with a K1 and a K2 that could represent literally any of those, as long as you make the right choice for K1 and K2. One two-parameter family of equations to represent the infinite number of curves that are in this plane right here. So let's go ahead and clear all these guys out of here. So where are the ones that we've been talking about? Well, we started one at 1, 0. So here's our first one. This is our y1 solution curve. And there it is. Notice that by making y be equal to 0, dy dt is 0. So there is no change in height ever. If y is 0, clearly our solution to the remaining part here is e to the 2t is going to be our other component, and that just says we grow away from the origin right there. Also, notice something really, really, really special. This isn't a curve. It's a straight line. How neat is that? You should say, that's pretty neat. Now I'm going to go ahead and check out the other initial condition that we had previously considered. The one to get our second solution here was negative 1, 2. And when I go ahead and graph that, oh man, how neat is that? It looks like that's actually a straight line also. How many other straight line solutions do you think there are out here in this phase plane? How many other straight line solutions do you think there are in this phase plane? Well, what I'm noticing here is I can certainly do things like swap my signs on this guy right here. Watch, I just change that to 1, negative 2. And if I do this guy, this just gets us sort of the other side of this line that we're generating right here. And very, very similarly, if I go to like negative 1, 0, I just get sort of the other side of that red curve right there. Now the purple one just showed up right there. So I'm seeing here that it looks like there is a straight line solution that's a horizontal line. I'm seeing a straight line solution that's this diagonal line. And what I'm seeing is that there are no other solutions out here in space that are also doing the same thing. All the rest of them out there are curves. All the rest of them are curves that you don't recognize the equation of. There are two lines out here, two curves out of an infinite number of curves where you could look at it and tell me the equation of it. And those happen to be the ones that we've been exploring here. It's not just random chance that those are the ones that the book suggested that we look at in 2.3. They were thinking ahead to 3.1 and really to 3.2, section 3.2, to set us up for the smartest possible solutions that we could have hunted for. Now, the real question is, how did they know that those were going to be the initial conditions that gave us the straight line solutions right here out of all the solutions? And that's exactly what we're going to talk about in the next section. So a really important thing that I want to do right now is I want to clear these curves right here. And in fact, I guess I kind of want to, well, let me do this one. Let me do this one. And then we want to do, what was it, negative 1, 2. And then its mirror image right there. So those are all of our straight line parts. What we were interested in doing is coming up with the one that was going through 2, negative 3. So let's see that guy. Here's 2, negative 3. So what our claim is that this equation that we just produced by finding those K1s and K2s is that guy. This orange curve right here is what we are claiming is that Y5 solution that we just came up with right there. So let me go ahead and snip this guy so I can throw this into our notes here. Okay, let's pop back over into Word here and throw this into our notes. All right, so our claim here. So I want to mark several things on this graph. So what we had right here was that this right here. All right, you're gonna have to let me do this word. This is my word challenge of the day right here. Will Microsoft Word allow me to draw on this graph? Here we go. Here we go. Oh, so far the answer is no. Okay, and it's still no. Can't even draw on the page right now. Okay, we're drawn, and we're drawn, and we're not drawing. Are you aware that we're doing stuff here? Am I allowed to type? Yes, I am. I am back being allowed to write again, so that's good. Still allowed to write, that's good. So, initial condition of interest 1, initial condition of interest 2. This is our 1, 0. This is our negative 2, 1. This green curve right there, that's our y1 of t. This blue one right here, that's our y2 of t. And our claim is that this guy right here, that started at 2, negative 3, is our y5 of t. This is our 2, negative 3. Now what we just did is we just found the K1 and K2 that we thought made that curve happen. And if that really was correct for our K1 and K2, then this set of parametrically defined equations should generate exactly this orange curve if we go to look at that curve in Desmos. So let's go ahead and see how do we do that in Desmos and kind of confirm that we're looking at the right thing right here. So this is the equation. This is the parametric equations that I want to define in Desmos. But you should notice Desmos is not down with doing like x of t equals and y of t equals. But what Desmos is down with doing to do parametric graphs is you can plot it sort of like as a point, x comma y, but we define them in terms of t, and it'll take those equations in that format right there. So let's pop over to Desmos and check this guy out. So we're going to graph x as 1/2 e to the 2t plus 3/2 e to the negative 4t. We're going to graph y as negative 3 e to the negative 4t. And what we're expecting to see Desmos do is generate this orange curve that we're seeing over here. Let's go ahead and do that. So over here now in Desmos, what I'm going to do is in Desmos form, what it wants, and this isn't going to work right now, I'm just showing you what my format's going to look like. This is how I'm going to plot this. X stuff, comma, Y stuff, and it's going to produce a curve. We just need to give it what X values and Y values we have found to make this guy happen. So what I'm going to do is I'm going to throw in our X equation that we had found, which is the 1/2 e to the 2t plus 3/2 e to the negative 4t. There's my x equation. I'm going to put in my y equation here, and it was negative 3e to the negative 4t. And oh yeah, there's that curve that we were looking to see right there, and I'm going to make t go from like negative 10 to 10 or something so we see more of it. And this is exactly where we were at here. I think that when we were looking at this guy in at the Bluffton site, we were going from negative 4 to 4 and from negative 3 to 3. And so this should be our same viewing window right there. And this looks a ton to me like that curve that we're just seeing right there, right? So hopefully you are feeling pretty good about this guy right there. Oh, I wish that you guys could act. So whatever. I've got a little bit more cut off right there. And this is not, okay. It's doing weird things to us a little bit. You can see that our X scaling and Y scaling aren't quite right there. In any event, with appropriate rescaling of our X and Y axes to match, this is exactly that same curve that we were looking to come up with right there. So let me just make this be in steps of 1, and I'm going to throw this graph also into, yeah, see, just doing that kind of like made it more square. Gosh, I wish I could, what if I do this? Oh, they're getting to be more and more square. Okay. Now, and again, I'm gonna do, oh, okay, there we go. Now this is looking quite a bit more like what I was expecting to see right there. Good. Good. Oh, sorry, but I do want this equation in here because I do want to make sure that we see how to do this. I'm going to drag this up here, and now I'll take a snip of this guy. Cool. All right. So there it is. There's our y5 of t. Cool. I'm going to give that the big check mark right there. There we go. Sorry. There we are over here in Word. Cool. So our graphs appear to clearly match each other. The solution that we found by linear combinations does match just the numerically produced solution. And remember, bluffton.edu, the Python code that we wrote, it doesn't know this equation. It doesn't know these functions right here. But we produce those functions by solving for the right K1 and K2 by doing just the easiest little bit of linear algebra right there. That was really easy for us to come up with this K1 and K2 and pass through the desired initial condition, which allowed us to state the equation of this guy right here. So now that we've got the linearity principle, we can now say what's the most general form of any solution to the given system of differential equations. Well, it should just be our general y of t equals k1 y1 plus k2 y2. Or we could write this as k1, our y1 equation was the e to the 2t 0, plus k2. This was our, that would be scrolling up 1,000 more times, negative e to the negative 4t, and a 2e to the negative 4t. And finally, we could probably write this as y of t equals, and get it all together here, k1 e to the 2t minus k2 e to the negative 4t. That's our x solution. Our y solution is 2k2 e to the negative 4t. And remember that that's our x solution and our y solution. We need to know what x and y are, since those are the two dependent variables in our system right there. Notice one thing real quick right here. We can't quite just let anything happen with our constants here. We've been doing a lot of like, let the constant absorb other nearby constants. But notice here, since there's multiple instances of K2 here, this K2, like if we just absorbed that negative right here, we'd need it to also like do some absorbing of a negative down here. And conversely, if this K2 just absorbed the 2 right here, then this guy's going to be off by a factor of 2 as well. So once we've introduced multiple different locations where a single constant coefficient like K1 or K2 is, you can't go just letting it absorb other nearby constant multiples right there. So that kind of has to stay in that format. But this now is a good general form for literally every single one of the infinite solution curves out there in the phase plane, which is really, really awesome, right? So again, I'm going to say, I've said it a couple times now, but I don't think we've kind of like felt the gravity of this thing yet. If you can find any two solutions, y1, y2, as long as they're not just constant multiples of each other, as long as they're actually linearly independent, then you should be able to take any linear combination of them to find another solution. And even more powerful than that, all solutions will be constructed by a linear combination of those two solutions that you've previously found. So what this says to me is this: if I want to find the general solution to any linear system of differential equations, all I ever have to do is find two solutions and verify that they're linearly independent. And then we can just take all linear combinations of them and we've got everything. So we've boiled down our problem of finding a general form for an infinite number of solutions to a system to just saying all we got to do is find two, verify that they're linearly independent, combine them with K1 and K2, and we've got everything. That's really, really, really powerful here. This linearity principle is wildly important for this this chapter to be manageable and not a graduate level topic here. So again, what we're going to say tomorrow in section 3.2 is, what solutions would we like to find? And the answer is going to be, well, the easiest ones. And what's the easiest curves to find in space? The straight ones. So that's what we're going to go hunt for in 3.2. And we're going to see, again, this is going to boil down to a linear algebra problem, not a calculus problem. In fact, what you're going to find is, I would go so far as to say I'm pretty sure that this on the screen right here represents the sum total amount of calculus we're going to do in all of chapter 3, which is really kind of nice right here. Taking a derivative to verify a solution. That's it. I'm trying to think right now. I'm trying to rack my brains. I think that we will never compute an integral for all of chapter 3. Is that true? I think that's true. We'll compute a couple derivatives. Who cares? Derivatives are freaking easy at this point, right? This is going to be all the power of our machinery. This chapter is linear algebra in a big, big way, and that's good. It is objectively a good thing for all of us here. So, as I've already said, our next question should be, what are the easiest two solutions we can possibly find for each system? The above graph is a pretty good hint. Notice that the two solutions that we found to help ourselves were the linear solutions right there. Our goal is going to be to find any linear solutions that exist in the system and then just take all their linear combinations to get all the other solutions that are out there, which is really cool. So I want to just show one last quick little example right here. This one should be pretty fast right here. I know that I'm already over at about an hour and 20 minutes right now, but this is a pretty cool little example to see that kind of justifies the things that we've been doing, uses the notation that we've been using here. So remember our undamped, meaning there's no damping force, there's no friction, there's no air resistance. Our undamped harmonic oscillator has this general form where there is a second derivative term representing acceleration, there is an x term representing position, but there's no damping force, and damping forces are influenced by velocity, and you'll notice there's not a velocity term relating these two guys. So we've already looked at this. I think this was actually our first ever second order differential equation. And we said, listen, if I'm going to find some solution here, it looks like it needs to be that the second derivative of x is the same thing as negative x. And I ask you, do you know any functions where after taking two derivatives of the function, you have back the same function just with a negative attached to it? And we said, well, yeah, that's actually really easy. Our trig functions actually do that for us here. So I'm noticing here that one good guess, is that our x of t should be cosine of t. That seems to me to be a reasonable guess for me to make right here, right? And the reason I think that's a reasonable guess is because x prime of t is going to be cosine's derivative is negative sine, and therefore x double prime of t is going to be negative cosine, and therefore x double prime plus x equals 0 is really just giving us negative cosine of t plus cosine of t equals 0. So it looks like that's a good guess right there. That's a solution. That's a solution. That's one solution. How many solutions do you really think there are to this differential equation? I kind of am suspicious that there's an infinite number of them, just because we've seen everything that's happening in our phase plane plotters out there. I mean, have you ever seen a time where there was like only one curve that existed in space? No, you just keep clicking and it keeps on generating more curves that are also solutions. Now, since you're an educated person, I should say to you, all right, we found one good guess. Can you make for me a second guess that you think will also work out here? Well, I think any reasonable person right now would say another good guess would certainly be x of t equals sine of t. So, just by making some really good guesses right here, we found two solutions. Oh my gosh, we found two solutions. Now, can you just add or subtract or take constant multiples of sine to get cosine? No. So it seems to me like cosine and sine are going to be linearly independent of one another. So let's go ahead and take a look at what our system solution would look like for this guy. I'm getting ahead of myself. Let me write one more sentence here. All right. And actually, I think we're going to state a general solution, not to the system, so don't worry about that last part right there. So let's convert to a system of differential equations. All right, so there's our second order differential equation. What we want to do is convert to a system, and we're going to do this the exact same way every single time. I'm going to first say that the derivative of x, and a very typical thing to do is to call that v, because I'm thinking of x as being position, and therefore v would be velocity. We can call this any variable that we want right there, but that's fine. Then I'm going to say that the derivative of v with respect to t, well, notice that the derivative of v is the second derivative of x. So that's really just negative x according to our original system right there. What is x double prime? According to our original system, it's negative x right there. So it looks like what we've come up with here is dx dt equals v, dv dt equals negative x. There's our system of linear differential equations right there. And by the way, I think that we can then go ahead and rewrite this by saying our capital F of y is equal to. And we want our A matrix here. What's our A matrix look like? Well, it looks like we want X first. How much X is in the first one? 0. How much V is in the first one? 1. How much X is in the second one? -1. How much V is in the second one? 0 times XV, right? That's my matrix representation of this guy that we're looking at here. Sorry, I gotta scroll the screen here. Okay, so what do we want to show here? Well, let's go ahead and look at our x1 solution. First, we guessed our first solution that we found was cosine of t, and so therefore v1 in our system should be negative sine t. So I'm thinking that our first solution, y1 of t, is the solution cos t negative sine t. Similarly, we found our second solution that we just guessed was sine t. That led us to our y2 of t to be cosine t. And therefore, I would say my vector y2 of t is our sine t cos t. Now, what I want to check out right here is I'm going to ask myself, are these linearly independent? Well, a really easy way to check this right here is to do not what I just wrote, but instead to say, well, what does it look like when you plug in 0? If I plug in 0, cosine of 0 is 1, negative sine of 0 is 0. For 2, if I look at times 0, where are we starting here? Well, this one's going to be at 0 and at 1, right? So the question is, are these linearly independent? What we're really asking is, could you construct this vector by taking constant multiples of this vector? And the answer is no. There's no constant that you could multiply 0, 1 by to get 1, 0 right there. Because you can't multiply something by 0 and get away from 0. The only thing you can multiply 1 by is 0 to get 0, but if you multiply 0 by 0, you also get 0 here, and we need a 1 there. There's no way to add, to multiply by a constant on one of these to get to the other. So these are linearly independent from one another. If you're a linear algebra person that's already taken linear algebra, then you should recognize these as our essential basis for R2, right? We can get to any location in the two-dimensional plane by just taking linear combinations of just these two vectors. This is what we call I and J if you're a physics person, really all of our vector notation, stuff like that. So we're going to say, yes, linearly independent. Therefore, x of t equals k1 cosine of t plus k2 sine of t is the general solution. So this is saying to me now things like 15 cosine of t minus 13 sine of t, that's going to work here also. And if you go ahead and plug that in for x, it's going to work out. And I think the other thing we could say here is we could say, and x of t, y of t, or sorry, that should be a v of t. Equal to k1 cos t plus k2 sine t. Notice that's xt is that. To get vt, we just take the derivative, so that should be negative k1 sine t plus k2 cos t is the solution in system form. All right, so linearity principle, it is the driving thing that's going to get us all of our general solutions for this entire chapter. Super, super important, really easy also. If we can find any two solutions and verify that those two solutions are linearly independent, which is really easy. Just plug in 0 for t and ask yourself, could I come up with one of them by taking constant multiples of the other? If we had found here like 1, 0 and 3, 0, then we'd be in trouble. These would just be two alternate representations of the same solution. And so we hadn't really, in fact, found two unique solutions right there. We need to find two linearly independent, distinct solutions, our linear algebra way of saying distinct solutions. And if we can, then we can take all constant multiples of all of their sums and differences, and that will represent all possible solutions that we'll ever see out in phase space out there. So again, our big motivator leaving this video is to say, our job for the rest of this entire chapter is find two solutions, and then you'll know everything that there is to know about the solution set for this problem. It's going to help us do things like classify all the equilibria that we're going to find at the origin. Remember, in most all cases, these are only going to have one equilibrium at 0, 0. It's very much going to be a special case when we identify an equilibria anywhere else. Finally, my last takeaway from today is this is all very specialty. We're talking our linear, two-dimensional system of differential equations. Only one derivative being taken. All these like specialty applications to this. But again, you should trust that what we're going to spend chapters 4, 5, and 6 doing is saying, oh, and by the way, all this stuff will apply to all these other scenarios aside from your specialty one. We're just kind of looking at the most manageable case right now and introducing the linear algebra concepts. So that when we get to the harder things later, we can say, oh, it's the same as that chapter 3 thing. Just tweak your result a smidge because of this one component right here, right? So this is very specialty, but it is going to broadly apply to lots of other concepts that we're going to see here coming up. So linearity principle is the number one thing for us to remember for chapter 3. It only applies to linear systems, but it gets us everything we want from linear systems. So next video, section 3.2, we're going to talk about how do we get those easy to find solutions. And since we're the laziest people around, I want to get the easiest two solutions that I can to build my general solution from those guys, so that we have our general solutions to all of our systems of linear differential equations here. I will see you guys for our second video, 3.2, in the next video. Have a good one.